This is the second session on power system protection. My name is Antonio Lima, and I will be hosting this session. I'm a professor at the Federal University of Rio de Janeiro. And let me call the first paper. It's called Phasor-Based Fault Location Challenges and Solutions for transmission lines equipped with high-speed time domain protective relays. It will be presented by Dr. Felipe Lopes, who was born in Brazil in 1985. He received the bachelor's, master's, and PhD degrees all in electrical engineering from the Federal University of Campina Grande, Brazil in 2009, 2011, and 2014, respectively. In 2014, Dr. Lopes joined the Department of Electrical Engineering, University of Brasília, Brazil. His research interests are electromagnetic transients, fault locations, and power system protection. Felipe, you have the floor. I ask you to share your presentation, share your screen with your presentation.
Okay, thank you. I am trying to share my screen. I think, yeah, it's nice. Okay. Okay, do you see my screen? Hello, do you see my screen?
I don't.
Oh, I'm sorry. I'm trying to do it again. Yeah. I'm sorry. I don't know what's the problem because okay. I'm so sorry about that. I'm having troubles to allow this sharing here. No? You can see my screen now?
Yes, I see it.
Oh, great. Thank you. Oh, I'm sorry about this delay. And I'd like to thank the Mr. Chair for the nice introduction. And my name is Felipe Lopes. I'm from the University of Brasília. And this paper is part of some of the first results that we have obtained in a major research on fault location solutions that has been conducted in partnership between the University of Brasília and Itaipu Binacional. We have noticed that time domain protection have gained importance in the market in the last years, and so now high-speed fault detection in the order of 4 milliseconds is a reality in our systems. And so we are expecting to verify some reduction of the fault duration, and depending on the circuit breakers, we are expecting that this fault period can reach the order of 1 power cycle only. Concomitantly, fault location procedures are still very important for utilities, and among the existing technologies, phasor-based techniques are still the most used, which in turn require measurements from the fault state. So that's a problem that is, to our best knowledge, this is a problem that is scarcely reported in the literature so far. And so our goal in this paper is to answer this question, how we can deal with reduced fault state period when phasor-based fault locators are used. So we have 2 main goals here. The first one is to evaluate the performance of phasor-based fault locators in case of reduced fault periods And the second one is to identify practical solutions that can be applied in the field, considering existing technologies and maybe some new concepts. In order to better illustrate the problem that we are studying here, let us consider firstly a traditional phasor-based protection being applied in a given line in which traditional circuit breakers are installed. The fault period duration will be given by the sum of the protection tripping time and the circuit breakers opening times. Protection tripping times, when we use phasor-based functions, is of about 1 to 1.5 power cycles, and circuit breakers open times, we can say that they can vary from 2 to 4 or 5 power cycles. But when we consider protection functions based on the fundamental component, we have a time to wait the phasors to stabilize, which depends on the data window length used during the phasor estimation process. And so then we have the operation. But when we are talking about fault location, the fault distance estimations must be taken only after such a phasor stabilization time. So in average, we typically have a fault location window larger than two power cycles. But what is the concept of time domain relays? It is simple. They just do not analyze phasors. And so if we use high-speed time domain protection associated with high-speed circuit breakers, we know that circuit breakers are evolving to be faster than those used in today's technology. The fault period will be reduced as well. The phasor stabilization time is removed from the protection tripping time, but it cannot be removed from the phasor-based fault location process in such a way that fault location windows shorter than 1 power cycle are expected. In order to demonstrate such a problem, which is still scarcely reported in the literature, we modeled a simplified power system, but just to generate contract files in order to test some actual devices. Basically, ADP fault simulations were performed, generating contract files, which were then adapted in order to perform a playback test into real time domain relays, from which traveling wave-based fault location estimations were obtained, and also the protection, the high-speed protection tripping times, which were combined with different circuit breakers opening times, which are taken here as 1 and 2 power cycles, considering some recent reports regarding high-speed circuit breakers. This, by considering these preliminary results, we adapted all ADP fault simulations in order to obtain new contract files, which were then used to evaluate the phasor-based fault location functions available in a traditional relay. Here are the results of this first part of the test case. You can see that we analyzed 2 different fault inception angles. We varied the fault distance. Here in purple, you can see the protection tripping times, which were very fast in our evaluated case. And here we are varying the circuit breaker opening time. As you can see here, in green color, when we consider that the fault duration is of about 2 power cycles, you can see that the fault location results are quite promising. But when the fault period is reduced to about 1 power cycle, these errors increase significantly. Regarding the traveling wave-based fault location method, as you can see here, when we have transients induced by the fault, like faults initiated close to the voltage peak, the results are amazing. Very accurate function were used here, errors of about 20 meters only. But in case when the transients are overdamped, these algorithms are not expected to operate. So we need further development in that. So as a first conclusion, we can say that, okay, if you have a reduced fault period, you can use traveling wave-based techniques. But if you do not have transients, you have another way to analyze those phasor-based fault location estimations available. So from the evaluated case, we saw that the estimated fault distance tends to oscillate around the actual fault distance in such a way that we are proposing here to represent these estimations as box plots. By doing so, we can identify the outliers and also other indexes that can be used as the final fault location. So we will analyze which of them are the most promising. And also we can estimate some search fields. So we are looking toward these search fields as well. And also we wanted to answer this question, is the mean value a good choice? Because a lot of devices use a weighted mean value or only a pure mean value as the final fault distance. So we analyzed this problem as well. To do so, an RTDS was used to simulate different fault cases in the same test system, from which an actual DFR was fed by voltage and current signals estimating phasors, which were then externally processed by a computer program responsible to calculate the box plot representation of the fault distance estimations obtained by means of 4 methodologies, among which we analyzed 1 single-winded method and 3 double-winded methods. Besides, 2 data windows were taken into account. The first one considering the whole fault period, and the second one by removing the phasor stabilization time to see the benefits of such a procedure. Regarding the case, we evaluated AG fault scenarios considering a loading angle equal to 13 degrees. The fault distance, fault inception, fault resistance were varied, and more important to know, we varied also the fault duration considering 1 and 2 power cycles. In the paper, there is a lot of detailed results, but here, due to time limitations, I will only discuss them briefly. Regarding the different fault periods and analyzed windows, when the fault duration of about 1 power cycle was taken into account, a very critical scenario was indeed verified for phasor-based fault locators. As I mentioned it earlier, the conclusion was that traveling wave-based techniques are suggested, or if they are not applicable, we could estimate some search fields by using the box plot representation. And here we indicate a topic that may be investigated in a future research with regard to the use of short window phasor estimation. Maybe we have to consider these algorithms in the future. When the fault duration equal to 2 power cycles were taken into account, obviously a better accuracy was obtained. But regarding this case, the removal of data during the phasor stabilization time, which were mapped as outliers, improved the fault location via the box plot indexes. And among the indexes estimated by this representation, we have had a surprise when we saw that the median value was the most promising, not the mean value. There is a little difference between these 2 indexes. Okay, regarding the estimated search fields, when the very short fault period was taken into account, the search field estimation provided some useful information, but we still have a very challenging scenario, because when we remove the phasor stabilization time from the analyzed time window, only few samples remain available in order to estimate these search fields. But even so, the performance, some useful information was obtained when 2 terminal methods were applied. here we illustrate the number of cases which took place within the estimated search field when I consider the first search field in between the upper and lower quartiles of the box plot, and also in between the maximum and minimum value. But here, even even considering the whole fault period, we had this percentage here of the reliability rate. And considering a less advanced case, but a still critical case with the fault duration equal to 2 power cycles, we had more data, so a better performance was verified. But in this case, the search field in between the maximum and minimum values, eliminating only the outliers, has shown to be more reliable, achieving a reliability rate in between 75% and 94%, even when we remove the phasor stabilization data. So as conclusions of this paper, in fact, the fault period reduction is challenging for phasor-based fault locators, so we have to think about it if we want to locate faults in case of overdumped transients. Obviously, when transients are launched on the line, are induced on the line, or when the traveling waves are launched on the line, the traveling wave-based methods partially solve the problem, but how to analyze voltage zero crossing case, for instance, it's a problem. In this case, circuit breakers, opening times, and fault inception instants are critical. And the future work we intend to analyze the use of short window phasor estimation for phasor-based fault location applications. But if the traveling wave-based methods are not applicable, the proposed statistic has shown to be promising. Obviously, we still have some challenging scenarios, but useful information could be taken from the box plot representation of all the estimated fault distances calculated during the evaluated case. The outliers removal has shown to be beneficial. The median value reduced the fault location errors, and the search fields provided useful information in most cases, indicating the region on the line where the fault probably is. Okay, that's all. Thank you very much for your attention.
Thank you, Felipe, for a timely presentation. It seems that there is no questions on the Q&A, but I have one question though. If you can go to your, I guess, second slide, I guess.
Yeah.
Yeah, no, the one after that. When you have, yes. Okay. If I understood you correctly, given you have a short time to realize all the fault location window, you also have a larger short circuit current with a larger DC component, right?
Yeah, that's it.
Have you investigated this impact in your algorithm?
Great question, Mr. Chair. Yeah, we have some impact of DC component on the estimated phasors. When we are now the evaluated case, we used some algorithms that are immune or mostly immune to the DC component, but that's a problem because even if I have 2 cycles, this DC component can be still present in the signal. But yeah, we have some oscillation that will appear due to such a component, and this is a problem. That's why the estimated fault distance sometimes oscillate around the actual fault distance, and that's why we are proposing to consider the box plot representation when it is possible.
Thank you. And another comment, you should investigate the impact on the actual circuit breaker, because it will deal with a larger current in future research, I mean.
Okay, thanks for your suggestion.
Okay, so let's move to the next presentation.
Let me stop the sharing.
Yeah.